All right, it is 10, so we will get started. So in case you didn't see my announcement on Blackboard, and I know many of you emailed me last night, there was a Blackboard outage for a little bit on Sunday. So what I will do for the assignments that were due today, you basically have until Tuesday at 10 to do them, in case you couldn't complete them. So that is the quiz, the reading guide, and the homework that were due at 10 a.m. today, or due right now. I'll just give you an extra 24 hours because of the whole Blackboard outage deal. All right. So let's continue on where we left off on Friday. So we were talking about our three different laws. So we talked about law of conservation of mass. Then we went to the law of definite proportions in the law of multiple proportions. The last thing we need to talk about on this slide before we move to the slideshow for today is Dalton in his atomic theory. So all these laws have been proposed. A lot of knowledge about chemistry has been tabulated in the 18th century. And by 1808, Dalton took all this information and he proposed what's known as the atomic theory. And the theory has four different parts. One, each element is composed of tiny indestructible particles called atoms. So 200 years ago, when it was this idea first proposed. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. So we'll see as we move on through this course, Dalton had most of it right, not everything right. We'll see something called an isotope, where atoms of the same elements actually weigh differently. Couldn't know that in 1808, so Dalton thought all atoms of the same element must weigh the same. Atoms combine in simple whole number ratios to form compounds. Yeah, they do. We don't have compounds that have like a half of an atom or a quarter of an atom. They're always in whole numbers. And atoms of one element cannot change into atoms of another element. And in chemical reaction, atoms only change the way they are bound together with other atoms. This is generally true. Generally, atoms can't just change into other atoms. They can change how they're bonded to other atoms, but they can't change themselves. And in Gen Chem 2, you're going to start learning about the exceptions to this, called nuclear chemistry, where we actually do see atoms changing to other types of atoms through a decay event. However, we don't need to be worried about such things right now. So throughout this whole semester, we're going to just ignore nuclear chemistry because that's at the very end of Gen Chem 2. And we're going to continue with atoms can't change. When you have a carbon going into a reaction, coming out of a reaction, you have to have a carbon as well. So here I have a question just to see if we understand what Dalton's theory said. So I have four different problems here, A, B, C, and D. I should have a poll for this. Yep. So they're basically true or false. So let me launch the poll. I want to know, based on Dalton's theory as presented, are these four different things true or false? Or in the first one is Fakasi, because I put a K7L. But yeah, and think about that. Think about Dalton theory, answer that, and we'll come back in a minute or so to discuss it. So we'll do about 15, 20 more seconds. So if you haven't answered yet, please do so. All right. So let's take a look at this. So there seems to be some confusion with A, because the majority of us said that, yes, according to Dalton's atomic theory, sulfur and oxygen do weigh the same. That is false. Number one's false. Remember, Dalton's theory says that each type of atom is unique. So sulfur and oxygen would be different. So they would have different masses. What he says is shown in B. All cobalt atoms are identical. That's true. So Dalton, if we could bring him back, he would say, yeah, sulfur and oxygen, different elements. So they have to have different masses. Cobalt, though, all cobalt are the same. So they would have the same masses. Like I said, we're going to learn in a little bit. That's not true, that cobalt atoms are not identical, but Dalton thought they were. So that is consistent with his atomic theory. Okay, so C, potassium chloride atoms combine in a 1-to-1 ratio to form potassium chloride. Yeah, that is consistent with his theory. He said that atoms combine in whole numbers to form compounds. So if they would form 1-to-1, that is consistent. So that is true. Lead atoms can be converted to gold atoms. That is false, right? Dalton's atomic theory said that, atoms can't change. If you have lead, it's going to stay lead. If you have gold, it's going to stay gold. The only thing you can change are how things are bonded to each other. And we have shown throughout time in history that alchemy isn't real. So there is no philosopher's stone. You can't find that and can change lead to gold. So any questions about Dalton's atomic theory or any of the laws we talked about on Friday and then here today? Okay, if not, I will move on to our next PowerPoint because that should be the last one of this slideshow. So let me move on to for February 1st. Hard to believe that January is already over. All right. So what we're going to talk about is we're going to move from atomic theory now to nuclear theory. And from the videos that you've watched on Blackboard, I talked about the experiments that went into nuclear theory. So I'm just going to kind of bypass that because there's not much more to say about the experiments that wasn't said in those videos. And let's just jump right into the theories. Right, so we have nuclear theory here, and this is proposed by Rutherford. And nuclear theory has 3 different parts to it. One, that an atom's mass and all of its charge are contained in a small core called the nucleus. 2, most of the volume of an atom is empty space. And throughout this empty space, you have tiny negatively charged electrons. It's really hard to think about like how empty an atom is. I guess a good example would be, let's take the auditorium at on campus. If you haven't been there, I don't know, it seats 150 people, maybe 200-ish. Like at the very max. Okay, so we're taking an auditorium that size. And we're going to say that whole space in the auditorium is an atom. The nucleus would be a marble in that space. So that's how small the nucleus is contained to the whole atom. And inside that empty space, you just have these electrons that are flying around. Those of you who really like science might know of the super colliders that we have around the world, where we speed up atoms super fast and try to collide them together. And that's actually kind of hard to do because you have to hit nuclei together. So it's like, take the example of having the marble in the auditorium. I'm going to be in the back of the auditorium throwing my marbles with a blindfold on, more or less, and trying to hit that center marble where I don't really know where it is. So not easy to do. And then the last idea of nuclear theory is that on the outside, there are as many negatively charged electrons as we have positively charged particles, which we call protons, in the nucleus. Not nuclease, that's an enzyme, that should be nucleus. So, and the atom is electrically neutral. Again, we're going to find that's not always the case. We have things that are called cations and anions, which are charged atoms. But in general, atoms, for the most part, stay neutral. They'll have the same number of protons and the same number of electrons. So 3 parts. You have nucleus, protons are in there, mostly empty, and around the atom you have electrons. So any questions about that theory? All right. So let's take a look at these subatomic particles that we now know of. Protons, neutrons, and electrons. So no matter what atom you're looking at, it's going to have these things. And those of you who are really interested in physics, you might already know this, you can break those things down even further. That's what you can do in one of those super colliders I was talking about. For general chemistry, we don't care about quarks and gluons. We care about protons, neutrons, and electrons. So for our discussion, especially in Gen Chem 1, we're going to say this is where it stops. Reality, it goes lower than that, but we're not going to worry about that. All right, so let's look at these subatomic particles. First, the protons and neutrons. I have their weight in kilograms, super small, times 10 to the minus 27. We never really talk about protons, neutrons, and electrons in terms of kilograms. What we use is the atomic mass unit, or the Dalton. So that's what AMU is, atomic mass unit. DA is the Dalton, named after Dalton. They're the same thing. It's just whatever word you want to use on any given day. So proton, neutron, weigh the same thing, or weigh the same rather. Electrons are tiny. If you look at their weight in terms of atomic mass unit, there's 0.00055, where a proton is 1. So they're so tiny. You never care about electrons when it comes to the weight of an atom. Because even if you had 100 electrons, or even have 200 electrons, that's not even 1% of the weight of one proton. So when we talk about electrons, we don't care about the weight. We care about the weight of protons and neutrons when it comes to atoms, but not electrons. But the cool thing is, or the interesting thing to me, is that the charge of the proton and the electron have the same magnitude, just opposite sign. So proton is positive, electron is negative, but they have the same, more or less, if I want to talk more in common words, they have the same voltage, just opposite signs of that voltage. And yes, matter, for the most part, is generally neutral. We're going to look at tons of examples where they're not neutral, but generally they are. The number of protons you have are equal to the number of electrons. So here, just to make sure, we're paying attention, just to make sure, in case you wandered off there for a bit in your mind to come back in, I have some more true and false questions to just see if we understand what was just said. Again, I have a poll here so I can just get a grasp of where we are in the class. So please take a minute or so to see, or just answer these and check our understanding of nuclear theory. So if you have any questions, let me know. Otherwise, I will be back in a minute or two with the answers. So we'll do about 30 more seconds or so. So if you haven't answered yet, please do so. All right, so let's take a look at this. And it seems, for the most part, we have a generally a good grasp on nuclear theory. So one, the volume of an atom is empty space. Yeah, that's true, right? That whole auditorium example I gave. So yeah, that's true. Nucleus of an atom is small compared to the size of the atom. Yep, that's true. Nucleus of an atom is tiny compared to the rest of the atom. Neutral lithium contains more protons than electrons. That is false, right? Remember, a proton has a positive 1 charge if you want to give a number. Electron has -1. Neutral means protons equal electrons. So if it's neutral, they have the same number of protons and electrons. Protons and electrons have the same magnitude, but opposite sizes of charge. That is true. That is the definition of protons and neutrons when related to each other. Protons have about the same mass of a neutron. That's also true. They weigh about the same. Some atoms don't have any protons. False. If an atom didn't have a proton, it's not an atom. It doesn't have a nucleus. So every single atom must have at least one proton. Electrons are much lighter than neutrons. True. Electrons have a tiny, tiny, tiny amount of weight. So any questions about nuclear theory as presented, or any questions at all from anyone? All right, we can move on then. So let's talk about isotopes then, which happens to be the name of the chemistry club here on campus. So if you would like, join the Jaguar Isotopes Chemistry Club. Anyways, what's an isotope? So when we look at atoms, let's say carbon atoms, the thing about a carbon atom is that they will always have the same number of protons. Like hydrogen atoms always have one proton. Helium atoms always have two protons. So looking at an atom of a given type, they have the same number of protons. That's what makes an atom a type of an atom, right? The moment you change the number of protons you have, then you have just fundamentally changed what atom you are. But atoms can have different numbers of neutrons. So when we look at carbon, they can have different numbers of neutrons when you compare two different carbon atoms. Hydrogen can have different number of neutrons when you compare hydrogen atoms. And we call these isotopes. So carbon has two main isotopes, like hydrogen has 3 isotopes. And when we talk about isotopes, we have certain notations we want to use. And that's shown here on this slide. And there are 2 different types of notations. So let me get up my periodic table. By the way, let me just mention this now. You will need a periodic table for this class to be successful, especially when we get into the calculations. You can't do the calculations without a periodic table. And so I have one up on Blackboard. It should be right under course contents. All right, so let's take a look at carbon, and I'm looking at my periodic table right now. So if you have one, feel free to pull it up. If not, that's okay. So carbon is the 6th element. So if you look on element number 6, you'll find carbon, and it has the symbol C, right? Now we have these things called atomic number and mass number. So atomic number is the number of protons in our atom. So no matter what carbon we're talking about, it will always have 6 protons. Carbon always has 6 protons. So that number always has to be 6. So atomic number, number of protons. Then above that, we put what's called the mass number. The mass number is protons plus neutrons. So there are 2 types of carbon. You have carbon with 6 neutrons, or you can have carbon with 7 neutrons. So the mass number is either 12 or it is 13. That's one type of way to write isotopes. Another way to write isotopes is you just put the symbol dash then the mass number. So you can have C12 or C13. The reason why in our second notation we don't have to put the atomic number is that if I put the symbol, it's already telling you the atomic number, right? Carbon always has 6 protons. If I was doing nitrogen, nitrogen always has 7 protons, and so on and so forth. Why are isotopes Why is it good to know about isotopes? Like, what's the point? We'll talk about this. I think we talk about this in Gen Chem 2. But one thing that's really cool about carbon is what's called carbon dating. And you might have heard about this before. The idea of carbon dating is that while a thing is alive, you have a certain ratio of carbon-12 to carbon-13. Let's just say for fun, I actually don't know the ratios. Let's just say while you're alive, you have 20% of carbon-12 in your body, you have 10% of carbon-13, right? And that will remain consistent as long as you are alive, because you're eating stuff, you're breathing stuff, so that ratio never changes. Once you die, or once an organic thing dies, what will happen is that this ratio changes, and it changes over time. And we know how fast it changes. It's a constant, right? So we can, if we find like a piece of cloth or anything that was once alive, and we see, oh, the carbon-12 in that sample is like 96%, and carbon-13 is like 4%. Based on experiments in our calculations, we can say pretty definitively how old that thing is. It's through something called half-lives, and it's something we'll talk about in Gen Chem 2. But that is one of the cool things about isotopes. You can use it to date things. So when you hear that the Earth is like 4 billion years old, how do we know that? Well, we found a really old piece of rock, and we can date it using different elements, or a dinosaur bone, stuff like that. Why is there different mass numbers again? So the different mass numbers comes from having different number of neutrons, right? Because the protons don't change. Carbon always has 6 protons. The mass number is protons plus neutrons. So in C12, we have 6 protons plus 6 neutrons equals a weight of 12, because a proton and a neutron weighs the same. In carbon-13, we have 6 protons plus 7 neutrons equals a total weight of 13. So that's where the different weights are coming from. Any other questions about the idea of an isotope? How do we know that there are 7 neutrons? Because if it's carbon, by definition, it has to have 6 protons, right? If it didn't have 6 protons, it's not carbon. And it's pretty easy to tell if something's carbon. Like it's carbon is very, one, it's the color, and 2, the way it feels. And you can do other experiments on it, but just by eye, I'm sure everybody here could actually spot carbon, because you all have looked at pencil lead, and that's basically carbon. But yeah, protons don't change in an element. With the atomic weight being 12.009 for carbon, do we just say that it's 12? We will get into how we do that. Short answer, generally you don't just say 12. But when you're talking about specific isotopes, so that I guess I will jump the gun a little bit and saying that 12.009 that you might see on a periodic table, that is coming from a calculation, and we'll look at that calculation. We'll learn that calculation. It's coming from a calculation where we say, we know we have this percentage of carbon-12. We know we have this percentage of carbon-13. Therefore, in a given sample of carbon, these percentages don't change. So the weight of carbon on average is 12.009. Like I said, we'll look at those calculations. When we're talking about isotopes, if I have a sample of carbon-12, the weight of that is 12, right? If I know 100% of that's carbon-12, it's 12. If I have a sample of carbon-13 and it's only carbon-13, the weight is 13. When we talk about elements in general, we can't round off the decimals like that because the decimals mean something. The decimals show us information. But like I said, we'll get to that. Any other questions about isotopes? All right, we will move on. Okay, well, here's something to test your understanding on isotopes. So for A and B, I want you to tell me the number of protons and the number of neutrons in the isotopes that I'm showing you. And then for C and D, write the isotope symbol in the form of X-A, like carbon-13 we just did for silver with 62 neutrons and hydrogen with 1 neutron. So at this point, you are going to need to get your periodic table. And let me, since it's if you haven't looked at a periodic table as much as I have, it's hard to find these elements first go around, so I'll help you. Hydrogen is element number 1. Silver is element number 47. Hope I don't have my gold and silver mixed up, but I think that's right. So yeah, see if you can figure this out. And if you have questions, let me know. But yeah, give you some time to do this and I'll come back with the answers. Also, if you want to check your answers with me, feel free to send me a private message as well, and I can just respond if you're right or not. In case you're completely lost, let me do it. If you do ever find yourself completely lost, please do let me know, and I'll be happy to help as much as I can. So A, we have this Rn compound. Remember what this says. This is symbol number of protons, the number of neutrons plus protons. So I want to know in A, how many protons are there? Well, it says right there, there's 86 protons. And then what are the number of neutrons? Well, neutrons plus protons equal 222. Well, I know the number of protons is 86. So neutrons plus 86 equals 222. Subtract 86 from each side, and the number of neutrons in this is 136. Therefore, for B, well, protons given 43. Protons plus neutrons equal 93. So neutrons plus 43 equals 93. Therefore, number of neutrons equals 50. For C, we go to our periodic table, see element 47. So you go to 47 and you see the element symbol. The element symbol of silver is Ag. And then we have a dash. So remember what the XA notation means. So the X is, what element is it? And the A is, again, protons plus neutrons. So silver is the 47th element. So that means it has 47 protons plus, and I'm telling you, it has 62 neutrons. So in total, 47 plus 62 is 109. So this isotope of silver is silver 109. D, hydrogen, one isotope, or sorry, one neutron. Hydrogen is the first element, so it has one proton. H2, one proton plus one neutron. All right, with that, is there any questions about our isotope notation or what an isotope is or anything along those lines? Okay, then we'll move on. So the next thing we're going to talk about are ions. So an ion is a similar concept to an isotope, but it's slightly different. So in isotopes, we were talking about atoms at the same number of protons with different neutrons. An ion is if the atom has the same number of protons, but different number of electrons. And you have positive ions. So remember, an electron is negatively charged. So that's something you should have burned into your brain. Electrons, negatively charged. Negatively charged. So always remember that. Electrons are -1. So if I start with 10 protons and 10 electrons, I'm neutral. If I lose an electron, so if I go from 10 protons to 9 electrons, my overall charge is +1 because protons are +1, electrons are -1. If you have a positive charge, you're called a cation, which is the cutest ion you will ever see. How to remember cations are positive? So let me stop the video or let me stop sharing because it works better in video format, I guess, or you can see me format. Right, so cations are positive. Get it? Positive, positive, cute, cat, positive, paw, cat. Yeah. So remember that. If you are ever thinking, is a cation have more protons or more electrons? Just remember cats have paws, positive, more protons. All right. So that's me making a fool of myself for today. You're welcome. That's what your tuition goes towards. And it's forever captured on YouTube now. All right. So what's a negative ion? A negative ion, I don't have a good acronym for this. They're called anion. So if we go back, 10 protons plus 10 electrons equals 0. Well, I gain more electrons. I gain one more. So 10 protons plus 11 electrons. Remember, protons are +1, electrons are -1. So overall, my charge is -1. This is called an anion. The best acronym I found for that is a negative ion, anion. In reality, what I do, or what I've done to remember this, is I just remember the whole cation business and remember the word anion, and no, anion's the opposite of that. But yeah, if you have more electrons, you're an anion. And when you're in an ion, you behave differently than your neutral counterparts. So lithium +1, as shown here. So the lithium cation behaves differently than neutral lithium. The fluorine anion, fluorine -1, behaves differently than neutral fluorine. So here I have a table for us. And we're, again, if you don't have a periodic table open somewhere, please go and do that. We're going to fill out a table to get familiar with our anions and cations. And I'm going to start with the first column just so we're familiar with this. So let me get my periodic table up. So we have the symbol calcium. And I'm telling you, in the ion we're looking at, calcium forms a +2 ion. So what I would do in this table is I would skip right to number of protons, because calcium is telling you how many protons it has by the element itself. So if you look on the periodic table, you're searching for the element Ca, and you'll find Ca as your number 20 element, right? So since it's 20, calcium has 20 protons. Now, how many electrons do we have? Well, I'm saying the overall charge is +2. Charge is given by protons minus electrons. So the number of protons we have are 20. Therefore, I have to do this math of 20 minus what equals 2. Well, 20 minus 18 equals 2. Therefore, the number of electrons we have are 18. So that's how I want you to fill out this table to get comfortable with ions. So I'll give everybody like a minute or two to get used to your periodic table and see if you can figure out these different ions. If you have questions, let me know. But I'll be back in a minute or two with the answers. All right, since we're running a little low on time, we're going to come back to this now. So on our second row, we have the ion Be2+. So again, we want to look on our periodic table and look for the symbol Be. Get my pen back out. So it's the symbol Be. That's easy to know once I give you the ion. So we'll see Be has 4 protons. For our third row, the ion is chlorine. Chlorine -1, and I'm saying there's 17 protons in it. Again, let's do the math. So protons minus electrons equals charge, right? So we have 17 protons minus electrons equals -1. Therefore, the number of electrons has to be 18. 17 minus 18 equals -1. And then our last row, it's a little bit different. I give you a number of protons, which is 11. So you go to your periodic table, you find the 11th element, that should be sodium, Na. Then I already tell you the number of electrons. So let's do this math. So protons minus electrons equal charge. 11 protons minus 10 electrons equal 1, a positive 1. Therefore, sodium is +1. Something with charges that's not obvious. If the charge is just +1 or -1, you just put the sign. You actually don't put the number there. If it's greater than 1, like we have our +2 or like -2, then you put the number. So if it's just plus or minus, you just put the sign. Greater than 1, the ion is greater than 1, you put the number. All right, so any questions about ions or our table here or anything along those lines? All right, well, that's basically all the time we have for today. So if you do have questions about anything, please let me know. Please email me. If I didn't respond to your email on Sunday, that's only because I got like 35 of them in the span of an hour. And so I knew it was a Blackboard issue. So I was hoping IT would send out something, and they did. But yeah, so do we have a question here? Dumb question. Well, there are dumb questions, but usually when it comes to chemistry, there aren't dumb questions. Dumb question, but it doesn't matter how we write the +2, like is it written +2 or 2+? It's usually written 2+, but it doesn't matter. So no, doesn't matter. All right. With that, I'll put a homework up. So same old, same old. Make sure if you haven't done it yet, do the assignments that were due today. Even though you do have an extension, don't forget about them. Don't forget about the stuff due on Wednesday. And otherwise, I will see everybody later. Have a good one, everybody. SI session at 2? Sounds good. Go to the SI session, get that extra credit.